you. So, in my talk, I will basically discuss two of our recent papers. The first one is this. So we did some electrical switching experiments on a metallic antiferromagnet, which is manganese nitride. I guess I don't have to introduce the electrical switching of antiferromagnets by now. I'm just bringing up some examples of switching experiments where the antiferromagnetic order has been manipulated with the spin Hall effect, basically due to the anti-damping spin transfer torque originating from the spin current that is injected into the antiferromagnet. And that allows you to manipulate the Néel order in antiferromagnets. So we looked into whether we can switch a metallic antiferromagnet, because all the other experiments that I've shown you have been done on insulating antiferromagnets. So our system is manganese nitride, which basically has the sodium chloride structure with a little bit of tetragonal distortion. It has a high Néel temperature, so you can do room temperature experiments with this. We grow our thin films basically on a tantalum seed layer on oxidized silicon substrates. So these are polycrystalline films, which are, however, nicely oriented with the manganese nitride growing along its 001 direction perpendicular to the film surface. Originally, we have done experiments on exchange bias with this material, and it turned out that we are able to get pretty large exchange bias fields, like 150 millitesla, with manganese nitride and cobalt iron as the ferromagnet. And also, we've done some proof of principle experiments to show the operation of a GMR spin valve with this antiferromagnet. So now we were interested in whether it's possible to electrically switch this material. So this is basically what we did. We took somewhat thinner layers of the manganese nitride. So here we went for 9 nanometers to exploit the weak anisotropy of the material. So at 32 nanometers, we get maximum exchange bias. So we were expecting to get a little bit easier switching at thinner films. This is why we went for 9 nanometers, and for comparison, we also did 6 nanometers. And then we grow a platinum layer on top of this. The electrical resistivities are around 200 microhm centimeters for the manganese nitride and the tantalum. The platinum has about 25 microhm centimeters, which means when we apply a voltage and pass a current through the stack, most of the current is going to flow through the platinum layer. So this is our source of the spin current. We use this standard 8-arm star-shaped device pioneered by Wadley and co-workers, originally proposed for the observation of the switching copper manganese arsenide. So this is our standard device that we use for the switching experiments. And then we actually performed our switching experiments and find that we can manipulate the transverse resistivity that we observe here in our probe configuration by passing current pulses along either the blue or the red direction here. So we have these background colors here in red or blue, which encode passing the current along this blue arrow or along this red arrow. And then we have these white backgrounds. This means there is no pulsing. This is basically just a relaxation time, and we just watch the transverse resistivity evolve in time and relax. We checked that this switching behavior is independent of polarity. So after a few cycles, we see that there is no more polarity dependence. So this is basically the signal. This average signal here is what we are going to look at. How do we do the data analysis? So we have basically 2 phases in our experiment. The first phase is the pulsing phase, where we increase this transverse response. And then we have this relaxation phase. So here our x-axis is the burst number that we send in. So burst consists of a number of pulses that we send in. And then we have this relaxation phase where the x-axis is simply time. We define this value here as the switching amplitude, or RA. And then we apply a simple switching model, which is simply phenomenological. So we just fit an exponential here and add a linear contribution. And this allows us to take the derivative here for the first few pulses very, very accurately by just looking at the analytic form of the fit. So we can look at the efficiency of the switching, which is basically this derivative here, by just looking at the coefficients of the fit. Then for the relaxation, we apply stretched exponentials, which have this form. So we have a constant plus an exponential where the time variable has an additional exponent. And from this, we can obtain a so-called stretched relaxation time from these parameters alpha and beta. And then we can calculate a mean relaxation rate, which is calculated with this expression, including the gamma function. And then having this parameter, we can calculate the energy barrier that basically leads to this relaxation behavior from the Néel-Arrhenius equation. Okay, now you can ask yourself, why do we use these stretched exponentials? Let's do some educational content here. These stretched exponentials basically always show up when you have ensembles of independent exponential decays, where these independent exponential decays have different relaxation rates. Let's have a look at a very simple example. Take 3 different exponentials with 3 different relaxation times, 10, 5, and 1. So the average relaxation time of these is going to be 5.33 and so on. Now you take the sum and try to fit a simple exponential, and you see, okay, this doesn't work because the sum of exponential isn't an exponential. Using instead this expression with a stretched exponential to fit the sum of these 3 exponentials gives you a very, very good agreement. And the reason for this is that there is a transformation that tells you that you can always rewrite an exponential as a stretched exponential as a continuous sum of exponentials. And from this, you get this mean relaxation rate. And from this fit, you can extract some parameters, beta and the stretched relaxation time. And when you now calculate the corresponding mean relaxation rate, this is 5.38 for this fit, which is very close to the exact solution that you would expect. So this is the beauty of the stretched exponentials, that they naturally include looking at an ensemble of multiple relaxation times. Okay, so now let's have a look at the temperature dependence and the current density dependence of the switching of this manganese nitride. First, let's have a look at the temperature dependence. So this is the left column where we extract the parameters I've just talked about. You immediately see that with increasing temperature, the amplitude of the switching goes up. And we see some difference between 6 and 9 nanometers. So for 9 nanometers, this amplitude is smaller and the peak is at higher temperature. Then the switching efficiency, which is the initial slope of the switching, is higher for the 9 nanometers film at higher temperature. But you see this nice shift of this, these curves. So for thicker films, you get the same efficiency only at higher temperatures. And then we look at the relaxation times and compare the 2 different film thicknesses and find that they are pretty similar. And by using the Néel-Arrhenius equation, we compute the energy barrier, and we observe that we observe that the energy barrier is basically the same for the 2 films, for 6 and 9 nanometers, which is a bit surprising actually. Okay, second, let's have a look at the right column, which corresponds to the bottom graph here. So we look at the current density dependence. So we see that as we increase the current density, so this is always the current density in the platinum film, from 7.5 to nearly 10 times 10 to the 11 amps per square meter, we see that the amplitude of the switching goes up. You see this nicely here. Correspondingly, the the efficiency of the switching, so this initial slope also increases, no surprise here, and the corresponding energy barrier is essentially flat, which means that there is no big change in the relaxation times that we see here. But as we go to higher current densities, we see that the relaxation times do increase to some extent. Okay, how can we now try to understand this in terms of the ensemble that I've talked about that contributes to this relaxation behavior? We did a grain size analysis with a plan view TEM imaging, and this is the results. So this is the probability distribution of the grain diameters, so the corresponding grain areas for a similar film. And our colleagues at York University did some exchange bias experiments with these films. So with a cobalt iron layer on top, they performed an anisotropy analysis via the York protocol, studying the exchange bias reversal in heating cooling cycles. And they find that the energy barrier at a thickness of 9 nanometers should be around 0.5 electron volts. And this is very similar to what we see in our experiments here, where we find that the energy barrier is 0.5 electron volts at low temperatures and increases to higher energy barriers at higher temperatures. So these numbers match up quite nicely. That's good. And this leads us to the conclusion that this probability distribution of grain diameters can be partitioned in basically 3 sub-ensembles, one of which we call unblocked, one is switchable, and one is blocked. What does that mean? The unblocked ensemble consists of grains which are, in a sense, super paramagnetic. So basically, the anisotropy is so weak that the Néel order basically just fluctuates randomly, and we're not able to observe this fluctuation. Then up here, there is this blocked part. So here, the anisotropy is so strong that the Néel order is always fixed. And no matter what we do with the current, we cannot rotate this Néel order because the anisotropy is too strong, so we cannot rotate. And then there is the switchable part. And the switchable part is which we actually switch. So when we apply our current and have the spin current acting on the magnetic moments, we can rotate the Néel order, but to some extent it will also relax. So this is the part of the ensemble that is actually switchable. Okay, in the literature, there have been some discussions about artifacts in these measurements. So we have been very careful about looking at artifacts in these measurements. And we looked at the repeatability of these measurements. So what we did is we looked at measurements at constant current density, but we did cycles. So we increased the current density, decreased it again, increased, decreased, and so on, and always looked at the same current density to see whether our results are repeatable. This is what we got. So after these cycles, so we have these this blue, black, green, and red traces here, and they look pretty much the same, which is good. But as we go to higher current densities, so here in violet and another green, we see that for very high current densities, we get this strange two-level behavior here of this relaxation part. When we zoom in, we find that here during the switching phase, it doesn't saturate anymore. But actually, we see that now this response goes down. Okay. And at the same time, we observe that the pulse line resistance, which is basically just the resistance measured along the pulse lines, increases as we go to higher current density. So you see these nice steps here when we increase our current density past a certain threshold value, which is around 1 × 10⁻12 amps per square meter. So as we go higher, we see that the resistance in the pulse lines increases. And here, finally, we just cranked up the current until the device ultimately broke. Okay, so it seems that this additional contribution that we're getting here is related to this increase in the resistance. So we decided to look into this phenomenon in more detail, and we looked at a system where we know there is no antiferromagnetic switching. And as an example, we chose niobium films, which we've grown on magnesium oxide substrates. We've grown them either at 400 degrees C or at room temperature. So we have a high temperature sample and a room temperature sample. The high temperature sample is epitaxial, the other one is polycrystalline. So this is what the XRD tells you. The high temperature sample has nicely 110 oriented growth of the niobium, whereas the room temperature sample has much smaller grains, as you can see here with the in the X-ray diffraction. Okay, then we did basically the same kind of experiment. We've structured these 8-arm devices. These are a little bit bigger in our case because we can't properly use electron beam lithography because these substrates are insulating, so they charge. So we avoided this by just using optical lithography here. And now we did a switching experiment. So this is our niobium film grown at room temperature, and we pulse it in this experiment with 7.5 times 10 to the 11 amps per square meter, and we find that we get a transverse response, very similar to what I've shown you before. But something odd happens here in this experiment. After a couple of cycles, this response vanishes, and then it seems to come back. But when you look closely, you see that the sign has changed. So here we have black and then red, so pulsing along this direction, then pulsing along this direction, gives up, down. And then later, this gives you down, up. Okay, so apparently the sign of our switching changes here, of our apparent switching. Then we also did the same experiment with niobium grown at 400 degrees C, so with this high temperature epitaxial sample, and we see that it just goes up, down, up, down, up, down, without any sign changes, no matter what we do with the current density. Okay, so you can ask yourself the question, what is going on here? Where does this signal come from? Okay, so we digged deeper. And our first idea among many, actually, so it wasn't really our first idea, it was one among many which we've tested, was that in these hotspots where the current flows through these narrow parts of the structure, the temperature should be pretty high during the pulsing, so that there might happen some recrystallization. So basically, it's a kind of annealing that's happening there. So to investigate this, we went to the advanced light source, beamline 1232, where you can do microdiffraction with a spot size of about 4 micron. And we did 2D diffraction experiments looking at these spots while doing a pulsing experiment. Very much the same as I've shown you before. And what we find here is that on the one hand, our signal to noise ratio is pretty bad. On the other hand, we see that there is a general trend for the intensity of our X-ray peaks to increase as we go through this experiment and pulse and pulse and pulse and pulse and so on. So generally, the intensity coming from these spots increases. In contrast, our high temperature epitaxial device doesn't do that. Here, the intensity is essentially flat. So yeah, so this is a part. Yeah, okay, so we can summarize this basically by saying, okay, so we have this Joule heating coming from the current, which is pretty from the current density, which is pretty large. This leads to a local annealing in these narrows of the structure, and this can lead to a reduction of the resistivity due to crystal growth. The high temperature sample doesn't do that because it is already nice and epitaxial, so there is nothing to crystallize, in contrast to our room temperature grown polycrystalline sample. Okay, so now we did some finite element simulations to understand this quantitatively. So this is our model for the FEM simulation. And now we just model this whole structure having a constant resistivity, with the exception of these narrows here, where we look at a either higher or lower resistivity. In this case, we model this with a lower resistivity to model this annealing effect. And we see that this leads to a transverse voltage drop when we pass a current through this probe line. So you can see this here in the asymmetry, and we have some voltage buildup plus and minus here. And this essentially comes from a broken mirror symmetry around this probe current. So when this mirror symmetry is broken, geometrically, you immediately get a transverse voltage drop, which is what we observe in our experiments. So this, unfortunately, is also present in simple Hall cross devices. So sometimes we do experiments with these simple devices passing currents like this. Very much the same behavior. So we have these hotspots here in these corners. We send the resistivity in this example to infinity, and we see again that we have this asymmetry in the voltage, which leads to these transverse signals. In addition to these experiments, we also did operando SEM investigations. So we looked at our structures in the SEM while doing the pulsing experiment. And we linked this to FEM simulations. So these traces here are what we see experimentally for the transverse response. Here is the longitudinal resistance of these pulse lines. So we see that our resistance first goes down, and as we increase the current further and further, the resistance eventually goes up again. And now we use our FEM simulation to calculate the transverse response, and we see that our transverse response follows pretty nicely the actually observed one. It's not exact, but you see that the qualitative behavior is very close, and these results are semi-quantitative within a factor of 2 or so. Okay, this is very nice. And in the end, we see that as we break the device, we see just before it breaks that something happens here in this narrow, I'm sorry, and finally, our device melts in this spot. So this is what the destroyed device looks like. So this gives us an indication that this destruction is due to electromigration just before the meltdown. Now we can estimate the destruction threshold through Black's equation of the mean time to failure due to electromigration. Black's equation says that the mean time to failure depends on 1 over j squared times an exponential with an activation energy. So as we increase the current density, we would get this blue line here. But due to the Joule heating of our current, we need to take the additional heat in the film into account. We do this analytically with this equation from this paper. And this gives us the red line here. And effectively, this gives us a dependence on the current density of j to the minus 13. Okay, so this is a very strong current density dependence that we get for the mean time to failure for our devices. And we find that in the end, our mean time to failure is about 1 microsecond at a current density of 2 × 10⁻12 amps per square meter, which is very close to what we observe experimentally. Okay, so from this, it is pretty clear that eventually the destruction of our device is due to electromigration. In summary, this means we have 2 ohmic contributions. First, we have, due to the Joule heating, a local annealing effect, and this leads to resistivity reduction. This is what we've seen here in this first part. And then, due to the high current density, we have some grain boundary electromigration. This leads to an increase of the resistivity because we destroy the grains, and eventually this leads to device failure. This leads to this opposite sign here. And finally, to this breakdown of the devices. So to summarize, this fake switching may be superimposed basically in any AFM switching experiment. And what one should always do in these experiments is check the reproducibility, check the pulse line resistances and look at possible changes there, and look for temperature-dependent relaxation, because when you see this temperature-dependent relaxation, it's very probable that you actually look at something that originates from the magnetic system. Okay, with this, I'm going to end my talk, and I would like to thank my co-workers from Bielefeld University, in particular Mareike Dunz and Tristan Matala-Wagner, who did most of the experimental work I've shown here in the paper, and also Dr. Jan Schmalhorst for assisting us with the ALS measurement, and Günther Reis for overall assistance and support during my time in Bielefeld. Okay, and I would like to thank you for your attention.